Week of 6046. Woohoo! The topic of this final week among our advanced topics is cache-oblivious algorithms. This is a particularly fun area, one dear to my heart because I've done a lot of research in this area. This is an area co-founded by Professor Leiserson. So, in fact, the first context in which I met Professor Leiserson was him giving a talk about cache-oblivious algorithms at WADS 99 in Vancouver, I think. Get that right? Yeah, it has to be an odd year. So I learned about cache-oblivious algorithms then, started working in the area, and it's been a fun place to play. But this topic, in some sense, was also developed in the context of this class. I think there was one semester, probably also 98, 99, where all of the problem sets were about cache-oblivious algorithms. And they were, in particular, working out the research ideas at the same time. So it must have been a fun semester. We considered doing that this semester, but we kept it to the single week. We know a lot more about cache-oblivious algorithms by now, as you might expect. Right. I think that's all the setting. I mean, it was co-developed also with a bunch of MIT students, in particular an MEng student, Harold Prokop, and it was his MEng thesis. There's all the citations I will give for now. I haven't posted yet, but there are some lecture notes that are already on my webpage, but I'll link to them from the course website. They give all the references for all the results I'll be talking about. They've all been done in the last 5 years or so, in particular starting in 99 when the first paper was published. But I won't give the specific citations in lecture. And this topic is related to the topic of last week, multi-threaded algorithms, although at a somewhat high level, in that it's also dealing with parallelism in modern machines. And we've had, throughout all but these last two lectures, we've had this very simple model of a computer where we have random access. You can access memory at a cost of 1. You can read and write a word of memory. There's some details of how big that word can be and whatnot, but it's a pretty basic, simple, flat model. And the multi-threaded algorithms, the idea is, well, maybe you have multiple threads of computation running at once, but you still have this very flat memory. Everyone can access anything in memory at a constant cost. We're going to change that model now. And we're going to realize that a real machine the memory of a real machine is some hierarchy. You have some CPU, you have some cache, probably on the same chip. Level 1 cache, you have some level 2 cache. If you're lucky, maybe you have some level 3 cache before you get to main memory. And then you probably have a really big disk. And probably there's even some cache out here, but I won't even think about that. So the point is you have lots of different levels of memory. And what's changing here is that things that are very close to the CPU are very fast to access. Usually level 1 cache you can access in like 1 clock cycle or a few. And then things get slower and slower. You know, memory still costs like 70 nanoseconds or so to access a chunk out of, and that's a long time. 70 nanoseconds is, of course, a very long time. And so as we go out here, we get slower, but we also get bigger. I mean, if we could put everything in level 1 cache, the problem would be solved. You know, that would be a flat memory. Accessing everything in here, we assume, takes the same amount of time. But usually we can't afford. It's not even possible to put everything in level 1 cache. I mean, there's a reason why there's a memory hierarchy. Does anyone have a suggestion what that reason might be? It's like one of these limits in life. Yeah. Fast memory is expensive. That's the practical limitation, indeed, that you could try to build more and more at level 1 cache, and maybe you could try to. Well, yeah, expensive is a good reason, and practically that's why it's maybe the sizes are what they are. But suppose memory were really fast memory were really cheap. There's a physical limitation to what's going on. Yeah.
The speed of light
like the speed of light. Yeah, that's a bit of a problem, right? No matter how much, you know, you can only fit, let's suppose you can only fit so many bits in an atom. You know, you can only fit so many bits in a particular amount of space. If you want more bits, you need more space. And the more space you have, the longer it's going to take for a round trip. So if you assume your CPU is like this point in space, so it's relatively small, and it has to get the data in, that the farther the bigger the data, the farther it has to be away. But you can have these cores around the CPU that are, you know, we don't usually live in 3D. In chips, we're usually in 2D, but never mind. You can have this sphere that's closer to the CPU that's a lot faster to access. And as you get farther away, it costs more. And that's essentially what this model is representing, although it's a bit approximated from the intrinsic physics and geometry and whatnot. But that's the idea. The latency, the round-trip time to get some of this memory has to be big. In general, the cost to access memory is made up of two things. There's the latency, the round-trip time, which in particular is limited by the speed of light, let's say. And there's plus the round-trip time, you also have to get the data out. And depending on how much data you want, it could take longer. Okay, so there's something, this would be, get this right, let's say the amount of data divided by the bandwidth. Okay, the bandwidth is at what rate can you get the data out. And if you look at the bandwidths of these various levels of memory, it's all pretty much the same. If you have a well-designed computer, the bandwidth should all be the same. Okay, so you can still get data off disk really, really fast, usually about at the speed of your bus, and then the bus gets the CPU, hopefully, as fast as everything else. So even though they're slower, they're really only slower in terms of latency. And so this part is maybe reasonable. The bandwidth looks pretty much the same universally. It's the latency that's going up. So if the latency is going up, but we still get to divide by the same amount of bandwidth, what should we do to make the access costs at all these levels about the same? What could, if this is fixed, let's say this is increasing, but this is still staying big. What could we do to balance this formula? Change the amount. As the latency goes up, if we increase the amount, then the amortized cost to access one element will go down. So this is amortization in a very simple sense. So this was to access a whole block, let's say, and this amount was the size of the block. So the amortized cost then to access one element is going to be the latency divided by the size of the block, the amount, plus 1 over the bandwidth. Okay, this is what you should implicitly be thinking in your head. So I'm just dividing here by the amount, because the amount is how many elements you get in one access, let's suppose. Okay, so we get this formula for the amortized cost. The 1 over bandwidth is going to be good no matter what level we're on, I claim. There's no real fundamental limitation there, except it might be expensive. And the latency we get to amortize out by the amount. So whatever the latency is, as the latency gets bigger out here, we just get more and more stuff, and then we can make these two terms equal, let's say. That would be a good way to balance things. So in particular, disk has a really high latency. You know, it takes, not only is there speed of light issues here, but there's actually the speed of the head moving on the tracks of the disk. That takes a long time. There's a physical motion. Everything else here doesn't usually have physical motion. It's just electric. So this is really, really slow in latency. So when you read something out of disk, you might as well read a lot of data from disk, like a megabyte or so. It's probably even old these days. Maybe you read multiple megabytes when you read anything from disk, if you want these to be matched. Okay, there's a bit of a problem with doing that. Any suggestions of what the problem would be? So you have this algorithm, and whenever it reads something off of disk, it reads an entire megabyte of stuff around the element it asked for. Is there some... I said the amortized cost to access is going to be reasonable, but that actually is sort of assuming something. Yeah. Right. I'm assuming I'm ever going to use the rest of that data. I better, if I'm going to read, 10 megabytes around the one element that I asked for, I access A bracket I, and I get 10 million items from A around I. It would be kind of good if the algorithm actually used that data for something. Seems reasonable. So this would be spatial locality. So we want, the goal of this world and cache oblivious algorithms and cache efficient algorithms in general is you want algorithms that perform well when this is happening. So when you read, so this is the idea of blocking. And we want the algorithm to use all, or at least most, of the elements in a block. A consecutive chunk of memory. So this is spatial locality. Ideally, it would use all of them right then. But that's, depending on your algorithm, that's a little bit tricky. There's another issue, though. So you read in your thing you read your 10 megabytes into main memory, let's say. And your memory, let's say, is at least, these days you should have a 4 gigabyte memory or something. So you can read in actually a lot of different blocks into main memory. What you'd like is that you can use those blocks for as long as possible. Maybe you don't even use them. If you have a linear time algorithm, you're probably only going to visit each element a constant number of times, so this is enough. But if your algorithm is more than linear time, you're going to be accessing elements more than once. So it would be a good idea not only to use all the elements in the block, but use them as many times as you can before you have to throw the block out. And that's temporal locality. So ideally, you even reuse blocks as much as possible. So we have all these caches. So I didn't write this word, just in case you don't know how to spell it. It's not the money. We should use those caches for something. The fact that they store more than one block. Each cache can store several blocks. How many? Well, we'll get to that in a second. Okay, so this is the general motivation, but at this point the model is still pretty damn ugly. If you wanted to design an algorithm that runs well on this kind of machine directly, it's possible but pretty difficult and essentially never done, let's say. Even though this is what real machines look like. At least in theory and pretty much in practice, the main thing to think about is 2 levels at a time. So this is a simplification where we can say a lot more about algorithms. A simplification over this model. So in this model, each of these levels has different block sizes and the different total sizes. It's a mess to deal with and to design algorithms for. If you just think about 2 levels, it's relatively easy. So we have our CPU, which we assume has a constant number of registers only. So, once it has a couple of data items, you can add them and whatnot. Then we have this really fast pipe, so I draw it thick, to some cache. So this is cache. And we have a relatively narrow pipe to some really big other storage, which I will call main memory. Right. So, I mean, that's the general picture. Now, this could represent any two of these levels. It could be, you know, between L3 cache and main memory. That's maybe what the naming corresponds to best. Or cache could, in fact, be main memory, what we consider the RAM of the machine. And what's called main memory over there could be the disk. I mean, it's whatever you care about. And usually, if you have a program, let's say, you know, usually we assume everything fits in main memory. Then you care about the caching behavior. So you probably look at between these two levels. That's probably what matters the most in your program, because the cost differential here is really big relative to the cost differential here. If your data doesn't even fit in main memory and you have to go to disk, then you really care about this level because the cost differential here is huge. It's like 6 orders of magnitude, let's say. So in practice, you may think of just two memory levels that are the most relevant. Okay? Now I'm going to define some parameters. I'm going to call them cache and main memory just for clarity, because I'd like to think of main memory as just the way it used to be. And now all we have to worry about is this extra thing called cache. It has some bounded size, and there's some block size. The block size is B. And the number of blocks is M over B. So the total size of the cache is M. Okay, main memory is also blocked into blocks of size B. And we assume that it has essentially infinite size. We don't care about its size in this picture. It's whatever is big enough to hold the size of your algorithm or data structure or whatever. Okay, so that's the general model. And for strange historical reasons, which I don't want to get into, these things are called capital M and capital B. Even though M sounds a lot like memory, it's really for cache, and don't ask. Okay, this is to preserve history. Okay, now what do we do with this model? Seems nice, but now what do we measure about it? What I'm going to assume is that the cache is really fast. So CPU can access cache essentially instantaneously. I still have to pay for the computation that the CPU is doing, but I'm assuming cache is close enough I don't care. And then main memory is so big that it has to be far away, and therefore this pipe is a problem. I mean, what I should really draw is that pipe is still thick, but is really long. So the latency is high. The bandwidth is still high. Okay, and all transfers here happen in blocks. So when you don't have something, and so the idea is CPU asks for A of I, asks for something in memory. If it's in the cache, it gets it. That's free. Otherwise, it has to grab the entire block containing that element from main memory, brings it into cache, maybe kicks somebody out if the cache was full, and then the CPU can use that data and keep going until it accesses something else that's not in cache, then it has to grab it from main memory. When you kick something out, you're actually writing back to memory. Okay, that's the model. So we suppose that accesses to cache are free. But we can still think about the running time of the algorithm. I'm not going to change the definition of running time. This would be the computation time, or the work if you want to use the multi-threaded lingo. Computation time. Okay, so we still have time, and T of n will still mean what it did before. This is just an extra level of refinement of understanding what's going on. Essentially measuring the parallelism that we can exploit out of the memory system, that when you access something, you actually get B items. So this is the old stuff. Now what I want to do is count memory transfers. These are transfers of blocks, so I should say block memory transfers, between the two levels, so between cache and main memory. So memory transfers are either reads or writes. Okay, maybe I should say that. These are number of block reads and writes. From and to main memory. Okay, so I'm going to introduce some notation. This is new notation, so see how it works out. MT of n, I want to represent the number of memory transfers instead of just normal time of the problem of size n. Really, this is a function that depends not only on n, but also on these parameters b and m in our model. So this is what it should be, mt sub b m of n. But that's obviously pretty messy, so I'm going to stick to mt of n. But this will always, because mainly I care about the growth in terms of n. Well, I care about the growth in terms of all things, but the only thing I can change is n. So in most of the time, I only think about, like when we're writing recurrences, only n is changing. I can't recurse on the block size. I can't recurse on the size of cache. Those are given to me. They're fixed. Okay, so we'll be changing n mainly. But b and m always matter here. They're not constants. They're parameters of the model. Okay. Easy enough. This is something called the disk access model, if you like damn models, or the external memory model, or the cache aware model. So maybe I should mention that. This is the cache aware. In general, you have some algorithm that runs on this kind of model, machine model. That's a cache aware algorithm. Okay, we're not too interested in cache-aware algorithms. We've seen one, B-trees. B-trees are a cache-aware data structure. You assumed that there was some block size B underlying. Maybe you didn't see exactly this model. In particular, it didn't really matter how big the cache was, because you just wanted to know when I read B items, I can use all of them as much as possible and figure out where I fit among those B items, and that gives me log base B of n memory transfers instead of log n, which would be if you just threw your favorite balanced binary search tree. So log base B of n is definitely better than log base 2 of n. B trees are a cache-aware algorithm. Okay, what we would like to do today and next lecture is get cache-oblivious algorithms. So there's essentially only one difference between cache-aware algorithms and cache-oblivious algorithms. In cache-oblivious algorithms, the algorithm doesn't know what B and M are. So this is a bit of a subtle point, but a very cool idea. You assume that this is the model of the machine, and you care about the number of memory transfers between this cache of size m with blocking B and main memory with blocking B. But you don't actually know what the model is. You don't know the parameters of the model. It looks like this, but you don't know the width, you don't know the height. Why not? So the analysis knows what B and M are. So we're going to write some algorithms which look just like boring old algorithms that we've seen throughout the lecture. That's one of the nice things about this model. Every algorithm we have seen is a cache-oblivious algorithm, right? Because we didn't even know the word cache in this class until today. So we already have lots of algorithms to choose from. The thing is, some of them will perform well in this model and some of them won't. So we would like to design algorithms that, just like our old algorithms, that happen to perform well in this context, no matter what B and M are. So another way of saying this is the same algorithm should work well for all values of B and M if you have a good cache-oblivious algorithm. Okay, there are a few consequences to this assumption. Okay, in a cache-aware algorithm, you can explicitly say, okay, I'm blocking my memory into chunks of size B. Here they are. I'm going to store these B elements here, these B elements here. Because you know B, you can do that. You can say, well, okay, now I want to read these B items into my cache and then write out these ones over here. You can explicitly maintain your cache. With cache-oblivious algorithms, you can't because you don't know what it is. So it's got to be all implicit. And this is pretty much how caches work anyway, except for disk. So it's a pretty reasonable model. In particular, when you access an element that's not in cache, you automatically fetch the block containing that element. And you pay 1 memory transfer for that, if it wasn't already there. Another bit of a catch here is, what if your cache is full? Then you've got to kick some block out of your cache. And then, so we need some model of which block gets kicked out, because we can't control that. We have no knowledge of what the blocks are in our algorithm. So what we're going to assume in this model is the ideal thing. That when you fetch a new block, if your cache is full, you evict a block that will be used farthest in the future. Furthest. Farthest is distance, furthest is time. Furthest in the future. Okay, this would be the best possible thing to do. It's a little bit hard to do in practice because you don't know the future, generally, unless you're omniscient. So this is a bit of an idealized model. But it's pretty reasonable in the sense that if you read the reading, handout number 20, this paper by Slater and Tarjan that introduced the idea of competitive algorithms. So we only talked about a small portion of that paper, the move to front heuristic, for storing a list. But it also proves that there are strategies, and maybe you heard this in recitation, some people covered it, some didn't, that these are called paging strategies. So you want to maintain some cache of pages or blocks, and you pay whenever you have to access a block that's not in your cache. The best thing to do is to always kick out the block that will be used farthest in the future, because that way you'll use all the blocks that are in there. This turns out to be the offline optimal strategy if you knew the future. But there are algorithms that are essentially constant competitive against this strategy. I don't want to get into details because they're not exactly constant competitive, but they are sufficiently constant competitive for the purposes of this lecture that we can assume this, not have to worry about it. Most of the time, we don't even really use this assumption, but there it is. That's the cache-oblivious model. It makes things cleaner to think about. Just anything that should be done will be done. And you can simulate that with least recently used or whatever good heuristic that you want to that's competitive against the optimal. Okay, that's pretty much the cache-oblivious algorithm. Once you have the two-level model, you just assume you don't know B and M. You have this automatic request and writing and whatnot. A little bit more to say, I guess. Maybe obvious at this point, but I've been drawing everything as tables, so it's not really clear what the linear order is. Linear order is just the reading order. So although we don't explicitly say it most of the time, a typical model is that memory is a linear array. Everything that you ever store in your program is written in this linear array. If you've ever programmed in assembly or whatever, that's the model. You have this address space, and any number between here and here, that's where you can actually, this is physical memory. This is all you can write to. So it starts at 0 and goes out to, let's call it infinity over here. And, you know, if you allocate some array, maybe it occupies some space in the middle. Who knows? Okay, we usually don't think about that much. What I care about now is that memory itself is blocked in this view. So however your stuff is stored in memory, it's blocked into clusters of length b. So if this is, let me call it 1, be a little bit nicer. This is b. This is position b plus 1. This is 2b, and 2b plus 1, and so on. These are the indexes into memory. This is how the blocking happens. If you access something here, you get that chunk from u rounded down to the previous multiple of b, rounded up to the next multiple of b. That's what you always get. Okay, so if you think about some array, that's maybe allocated here, okay, you have to keep in mind that that array may not be perfectly aligned with the blocks. But more or less it will be, so we don't care too much. But there's a bit of a subtlety there. Okay. That's pretty much the model. So every algorithm we've seen, except B-trees, is a cache-oblivious algorithm. And our question is now, we know how it runs, how everything runs in terms of running time. Now we want to measure the number of memory transfers, this MT of n. I want to mention one other fact or theorem. I'll put it in brackets because I don't want to state it precisely. But if you have an algorithm that is efficient on two levels, so in other words, what we're looking at, if we just think about the two-level world and your algorithm is cache oblivious, then it is efficient on any number of levels in your memory hierarchy. Say L levels. So I don't want to define what efficient means. But the intuition is if your machine really looks like this and you have a cache-oblivious algorithm, you can apply the cache-oblivious analysis for all B and M. So you can analyze the number of memory transfers here, 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 and here. And if you have a good cache-oblivious algorithm, the performances at all of those levels has to be good. And therefore, the whole performance is good. Good here means asymptotically optimal up to constant factors, something like that. Okay, so I don't want to prove that, but that you can read the cache-oblivious papers. That's a nice fact about cache-oblivious algorithms. If you have a cache-aware algorithm that tunes to a particular value of B and a particular value of M, you're not going to have that property. So this is one nice feature of cache-obliviousness. Another nice feature is you don't have to, when you're coding the algorithm, you don't have to put in B and M. So that simplifies things a bit. So let's do some algorithms. Enough about models. Okay, we're going to start out with some really simple things just to get warmed up on the analysis side. The most basic thing you can do that's good in a cache-oblivious world is scanning. So scanning is just visiting the items in an array in order. So visit A1 up to AN in order. For some notion of visit, this is presumably some constant time operation. For example, suppose you want to compute the aggregate of the array. You want to sum all the elements in the array. So you have one extra variable you're using, but you can store that in a register or whatever. So that's one simple example. Sum the array. Okay, so here's the picture. We have our memory divided. Each of these cells represents one item, one element, log n bits, one word, whatever. Our array is somewhere in here. Maybe it's there. And we go from here to here to here to here. Okay, and so on. So what does this cost? What is the number of memory transfers? We know this is a linear time algorithm. It takes n, order n time. What does it cost in terms of memory transfers? N over B, pretty much. I'd like to say it's order n over B plus 2 or 1 in the big O. Yeah. There's a bit of worry. I mean, n could be smaller than B. We really want to think about all the cases, especially because usually you're not doing this on something of size n. You're doing it on something of size k, where we don't really know much about k. In general, it's n over b plus 1. Because we always need at least one memory transfer to look at something, unless n is 0. And in particular, it's plus 2 if you care about the constants. If I don't write the big O, then it would be plus 2 at most. Because you could essentially waste the first block, and then everything's fine for a while. And then if you're unlucky, you essentially waste the last block. There's just one element in that block, and you're not getting much out of it. Everything in the middle, though, every block in between the first and last block has to be full. And so you're using all of those elements. So out of the n elements, you only have n over b blocks, because a block has b elements. Okay? That's pretty trivial. Let me do something slightly more interesting. Which is 2 scans at once. Okay, here we're not assuming anything about m. We're not assuming anything about the size of the cache. Just that it can hold a single block. We just need that the last block that we visited has to be there. Okay, you can also do a constant number of parallel scans. This is not really parallel in the sense of multi-threaded, but simulated parallelism. I mean, if you have a constant number, I do one, do the other, come back, come back, come back. Right? Visit them in turn, round robin, whatever. For example, here's a cute piece of code. If you want to reverse an array, okay, then you can do it. This is a good puzzle. You can do it by essentially 2 scans where you repeatedly swap the first and last element. So it's swapping AI with a n minus I plus 1. And this, if we start at 1. So here's your array. Suppose this is actually my array. I swap these 2 guys, and I swap these 2 guys, and so on. That will reverse my array. And this should work hopefully in the middle as well if it's odd. Should not do anything. And this, you can view this as a scan, as 2 scans. There's one scan that's coming in this way. There's also a reverse scan. Ooh, some more sophisticated. Coming back this way. Of course, reverse scan has the same analysis. And as long as your cache is big enough to store at least 2 blocks, which is a pretty reasonable assumption. So let's write it. Assuming the number of blocks in the cache, which is m over b, is at least 2, in this algorithm, the number of memory transfers is still order n over b plus 1. Okay, the constant goes up maybe, but in this case it probably doesn't, but who cares? Okay, it's, as long as you're doing a constant number of scans and some constant number of arrays, happens to be one of them's reversed, whatever, it will take, we call this linear time. It's linear in the number of blocks in your input. Okay, great. So now you can reverse an array. Exciting. Let's try another simple algorithm. On another board. Let's try binary search. So just like last week, we're going back to our basics here. Scanning, we didn't even talk about in this class. Binary search is something we talked about a little bit. It was a simple divide and conquer algorithm. Hope you all remember it. And if we look at an array, and I'm not going to draw the cells here because I want to imagine a really big array. A binary search, let's suppose it always goes to left. It starts by visiting this element in the middle. Then it goes to the quarter mark. Then it goes to the 1/8 mark. Okay, this is one hypothetical execution of a binary search. Okay, and eventually it finds the element it's looking for, finds where it fits at least. So X is over here. So we know that takes log n time. How many memory transfers does it take? Now I've blocked this array into chunks of size b, blocks of size b. How many blocks do I touch? This one's a little bit more subtle. Depends on the relative sizes of n and b, yeah.
Is it log base b of n?
Log base b of n would be a good guess. We would like it to be, let's say hope, is that it's log base b of n. Because we know that B trees can search in what's essentially a sorted list of n items in log base b of n time. That turns out to be optimal in the cache oblivious model, or in the two-level model. You've got to pay log base b of n. I won't prove that here to search. It's the same reason you need log n comparisons to do a binary search in the normal model. Alas, it is possible to get log base b of n even without knowing b, but binary search does not do it. Log of n over b, yes. Remember my own notation. So number of memory transfers on n items is log of n over b, also known as, let's say plus 1, also known as log n minus log b. Okay, whereas log base b of n is log n divided by log b. Okay, clearly this is much better than subtracting. So this would be good, but this is bad. Most of the time, this is log n, which is no better, which you're not using blocks at all, essentially. The idea is, out here, there's some little tiny block that contains this thing. Tiny depends on how big b is. But each of these items will be in a different block until you get essentially within one block worth of x. When you get within one block worth of x, there's only like a constant number of blocks that matter. And so all of these axes are indeed within the same block. But how many are there? Well, just log b. Because you're only spending log b with any log. If you're within an interval of size k, you're only going to spend log k steps in it. So you're saving log b in here. But overall, you're paying log n. So you only get log n minus log b plus some constant. Okay, so this is bad news for binary search. So not all of the algorithms we've seen are going to work well in this model. We need a lot more thinking before we can solve what is essentially the binary search problem, finding an element in a sorted list in log base b of n without knowing b. Okay, we know we could use B trees. If you knew B, great, that works. And that's optimal. But without knowing B, it's a little bit harder. And this gets us into the world of divide and conquer. Also, like last week, and like the first few weeks of this class, divide and conquer is your friend. And it turns out divide and conquer is not the only tool, but it's a really useful tool in designing cache oblivious algorithms. And let me say why. So we'll see a bunch of divide and conquer based algorithms, cache oblivious. And the intuition is that we can take our, all the favorite algorithms we have. Obviously, it doesn't always work. Binary search was a divide and conquer algorithm. It's not so great. But in general, the idea is that your algorithm can just do the normal divide and conquer thing, right? You divide your problem into subproblems of smaller size repeatedly, all the way down to problems of constant size. Okay, just like before. But if you're recursively dividing your problem into smaller things, at some point you can think about it and say, well, wait, the algorithm divides all the way, but we can think about the point at which the problem fits in a block or fits in cache. Okay, so that's the analysis. We'll think about the time when your problem is small enough that we can analyze it in some other way. So usually we analyze it recursively, we get a recurrence. What we're changing essentially is the base case. So in the base case, we don't want to go down to a constant size. That's too far. I'll show you some examples. We want to consider the point at which the time, or the recursion, at which either the problem fits in cache, so it has size less than or equal to m, or it fits in order 1 blocks. That's another natural time to do it. Order 1 blocks would be even better than fitting in cache. So this means it's size order B. Okay, this will change the base case of the recursion and it will of the recurrence, and it will turn out to give us good answers instead of bad ones. So let's do a simple example. Our good friend, order statistics, in particular for finding medians. So I hope you all know this by heart. Remember the worst case linear time median finding algorithm by Bloom et al. I'll write this fast. We partition our array. Turns out this is a good algorithm as it is. We partition our array conceptually into n over 5 tuples, into little groups of 5. This may not have been exactly how I wrote it last time. I didn't check, but it's the same algorithm. You compute the median of each 5 tuple. Then you recursively compute the median of the medians, of these medians. Then you partition around x. So that gave us some element that was roughly in the middle, is within the middle half, I think. Partition around x. And then we showed that you could always recurse in just one of the sides. Okay, this was our good old friend for computing order statistics or medians or whatnot. Okay, so how much time does this, well, we know how much time this takes. It should be linear time. But how many memory transfers does this take? Well, conceptually partitioning that I can do in 0. Maybe I have to compute n over 5. No big deal here. We're not thinking about computation. I have to find the median of each tuple. So here it matters how my array is laid out. But what I'm going to do is take my array, take the first 5 elements, and then the next 5 elements, and so on. Those will be my 5 tuples. So I can implement this just by scanning and then computing the median of those 5 elements, which I store in the 5 registers in my CPU. I'll assume that there are enough registers for that. And I compute the median, write it out to some array out here. So there's going to be one element, so the median of here goes into there, the median of these guys goes into there, and so on. So I'm scanning in here, and in parallel I'm scanning and outputting here. So it's 2 parallel scans, so that takes linear time. So this takes order n over b plus 1 memory transfers. Okay, then we have recursively compute the median of the medians. This step took, used to be t of n over 5, now it's mt of n over 5. Okay, with the same values of b and m. Then we partition around x. Partitioning is also like 3 parallel scans, if you work it out. So this is also going to take linear memory transfers, n over b plus 1. And then we recurse in one of the sides, and this is the fun part of the analysis, which I won't repeat here, but we get mt of like 3/4 n. I think originally it was 7/10, so we simplified to 3/4, which is hopefully bigger than 7/10. Yeah, it is. Okay, so this is the new analysis. Now we get a recurrence. So let's do that. So the analysis is we get this mt of n is mt of n over 5 plus mt 3/4 n plus, so this is just as before. Before we had linear work here, now we have what we call linear number of memory transfers, linear number of blocks. Okay, I'll sort of ignore this +1. It's not too critical. So this is our recurrence. Now it depends what our base case is. And usually we would use a base case of constant size. So let's see what happens if we use a base case of constant size, just so it's clear why this base case is so important. Okay, this describes a recurrence as one of these hairy recurrences. And I don't want to use substitution. I just want the intuition why this is going to solve to something rather big. Okay, and for me, the best intuition always comes from recursion trees. If you don't know the solution to recurrence and you need a good guess, use recursion trees. And today, I will only give you good guesses. I don't want to prove anything with substitution, because I want to get to the bigger ideas. So this is even messy from a recursion tree point of view, because you have these unbalanced sizes. Right? You start at the root with something of size n over b, then you split it into something size 1/5 n over b, and something of size 3/4 n over b, which is annoying because now this subtree will be a lot bigger than this one. Right? This one will terminate faster. So it's pretty unbalanced. But we can, and summing per level doesn't really tell you a lot at this point. But let's just look at the bottom level. Look at all the leaves in this recursion tree. So that's the base cases. How many base cases are there? This is an interesting question. We've never thought about it in the context of this recurrence. It gives a somewhat surprising answer. It was surprising to me the first time I worked it out. So how many leaves does this recursion tree have? Well, we can write a recurrence, right? Number of leaves in a problem of size n is going to be the number of leaves in this problem plus the number of leaves in this problem, plus 0. So that's another recurrence. Call this L of n. Okay, now the base case is really relevant. It determines the solution to this recurrence. And let's again assume that in a problem of size 1, we have 1 leaf. That's our only base case. Well, it turns out, and here you need to guess, I think. This is not particularly obvious. Any of the TAs have guesses of the form of the solution? Or anybody, not just TAs. But this is open to everyone. If Charles were here, I would ask him. I had to think for a while. It's not linear, right? Because you're somehow decreasing quite a bit. So it's smaller than linear, but it's more than a constant. Okay, that's about. It's actually more than polylog. So what's your favorite function in the middle? N over log n. That's still too big. Keep going. I have an oracle here, so you can. N to the k, yeah, close. I mean, k is usually an integer. N to the alpha for some real number between 0 and 1. Yeah, that's what you meant. Sorry. It's like this shortest mathematical joke. Let epsilon be less than 0. Or for a sufficiently large epsilon, I don't know. So you got to use the right letters. So let's just suppose that it's n to the alpha. Then we would get this, we would get n over 5 to the alpha, and we'd get 3/4 n to the alpha. When you have a nice recurrence like this, you can just try plugging in a guess and see whether it works. Okay, and of course, this will work only depending on alpha. So we should get an equation on alpha here. So that everything has an n to the alpha, in fact, all of these terms. So I can divide through by n to the alpha. So that's assuming that it's not 0 or something. That seems reasonable. So we have 1 equals 1/5 to the alpha plus 3/4 to the alpha. This is something you won't get on a final because I don't know any good way to solve this except with like Maple or Mathematica, or if you're smart, I'm sure you could compute it in a nicer way. But alpha is about 0.8, turns out. So the number of leaves is this sort of in between constant and linear. It's not really usually polynomial means you have an integer power. Let's call it a polynomial. Why not? There's a lot of leaves, is the point. And if we say that each leaf costs a constant number of memory transfers, we're in trouble. Because then the number of memory transfers has to be at least this. If it's at least that, that's potentially bigger than n over b. I mean, bigger than in an asymptotic sense. This is little omega of n over b if b is big. If b is at least n to the 0.2 something. Okay, or 1/7 something. But if, in particular, if b is at least n to the 0.2, then this should be bigger than that. So this is a bad analysis, because we're not going to get the answer we want, which is n over b. The best you could do for median is n over b, because you have to read all the elements, and you should spend linear time. So we want to get n over b. This algorithm is n over b, plus 1. So this is why you need a good base case, all right? Hopefully that makes the point. So the question is, what base case should I use? So we have this recurrence. What base case should I use? Constant was too small. We have a couple choices listed up here. Any suggestions? B. Okay, empty of B is the hard part. So if my problem, if the size of my array fits in a block, and I do all this stuff on it, how many memory transfers could that take? One. Or constant, depending on alignment. Okay, maybe it takes 2 memory transfers, but constant. Good. That's clearly a lot better than this base case MT of 1 equals order 1. Clearly stronger. So hopefully it gives the right answer. And now, indeed, it does. Yeah, I love this. So I'm going to wave my hands. Okay, but in particular, what this gives us, if we do the previous analysis, what is the number of leaves? So in the leaves, now L of b equals 1 instead of L of 1 equals 1. So this stops earlier. When does it stop? Well, instead of getting n to the order 0.8 whatever, we get n over b to the power 0.8 whatever. Okay, so it turns out number of leaves is n over b to the alpha, which is little o of n over b. So we don't care. It's tiny. And if you look at, and the root cost is n over b in the recursion tree. The leaf cost is little o of n over b. And if you wave your hands and close your eyes and squint, the cost should be geometrically decreasing as we go down, I hope, more or less. It's a bit messy because of all the things terminating. But let's say cost is roughly geometric. Don't do this in the final, but you won't have any messy recurrences like this. So don't worry. Down the tree. So I want to, you'd have to prove this formally, but I claim that the root cost dominates. And the root cost is n over b. So we get n over b. Okay, so this is a nice linear time algorithm for order statistics, for cache oblivious. Great. This may turn you off a little bit, but this is even though this is like the simplest algorithm, it's also probably the most complicated analysis that we will do. In the future, our algorithms will be more complicated and the analyses will be relatively simple. And usually it's that way with cache oblivious algorithms. So I'm giving you this sort of as the intuition why this should be enough. Then you have to prove it. Okay? Let's go to another problem where divide and conquer is useful. Our good friend matrix multiplication. I don't know how many times we've seen this in this class, but in particular we saw it last week with a recursive matrix multiply multi-threaded algorithm. So I won't give you the algorithm yet again, but we're going to analyze it in a very different way. So we have C, and we have A, and actually, up to you. So I could cover standard matrix multiplication, which is when you do it row by row and column by column. And we could see why that's bad. And then we could do the recursive one and see why that's good. Or we could skip the standard algorithm. So how many people would like to see why the standard algorithm is bad? Because it's not totally obvious. 1, 2, 3, 4, half. Wow, that's a lot of votes. And how many people would want to skip to the chase? No one. Oh, one. OK. And everyone else is asleep. So it's pretty good, 50% awake, not bad. OK, then, sorry, standard matrix multiplication. I'll do this fast, because it is, I mean, the basic idea, you all know the algorithm, right? To compute this value of C, in A, you take this row, and in B, you take this column. Sorry, I did that a little bit sloppily. But it's supposed to be aligned. Right? So I take all of this stuff, I multiply it with all of this stuff, add them up, the dot product. That gives me this element. And let's say I do them, in this order, row by row. So for every item in C, I loop over this row and this column of B, multiply them together. That is a access pattern in memory. So exactly how much that costs depends how these matrices are laid out in memory. Okay, this is a subtlety that we haven't had to worry about before because everything was uniform. I'm going to assume for the, give the standard algorithm the best chances of being good. I'm going to store C in row order, row major order, A in row major order, and B in column major order. So everything is nice and you're scanning. So then this inner product is a scan. Cool. Sounds great, doesn't it? It's bad, though. Assume A is row major. And B is column major. And C, you could assume, is really either way. But if I'm doing it row by row, I'll assume it's row major. So this is what I call the layout, the memory layout of these matrices. Okay, it's good for this algorithm, but the algorithm is not good. So it won't be that great. So, how long does this take? How many memory transfers? We know it takes n cubed time. I'm not going to try and beat n cubed here. Just going to try to get standard matrix multiplication going faster. So, well, for each item over here, I pay n over b to do the scans and get the inner product. So n over b per item. So so n over b. I'll ignore the +1 here. To compute each Cij, so that would suggest, as an upper bound at least, it's n cubed over b. Okay, and indeed that is the right bound. It's a theta. This is memory transfers, not time, obviously. That is indeed the case because if you look at consecutive, I do this Cij, then this one, this one, this one, this one. Keep incrementing j and keeping I fixed. Right? So the row that I use stays fixed for a long time. I get to reuse that if it happens, say that fits in a block, maybe. I get to reuse that row several times, if that happens to fit in cache. But the column is changing every single time. Okay, so each time I move here and compute the next Cij, even if a column could fit in cache, I can't fit all of the columns in cache. And the columns that I'm visiting move, they just scan across. I'm scanning this whole matrix every time. And unless your entire matrix fits in cache, in which case you could do anything, I don't care, it'll take constant time, or it'll take m over b time, enough to read it into the cache, do your stuff, and write it back out. Except in that boring case, you're going to have to pay n squared over b for every row here, because you have to scan the whole collection of columns. You have to read this entire matrix for every row over here. So you really do need n cubed over b for the whole thing. So it's usually a theta. So you might say, well, that's great. It's the size of my problem, the usual running time, divided by b. And that was the case when we were thinking about linear time, n versus n over b. It's hard to beat n over b when your problem is of size n. But now we have a cubed. And this gets back to, we have good spatial locality. When we read a block, we use the whole thing. Great. Seems optimal. But we don't have good temporal locality. It could be that maybe if we stored the right things, we kept them around, we could use them several times. Because we're using each element like a cubed number of times. That's not the right way of saying it. But we're reusing the matrices a lot. We're using those items. If we're doing n cubed work on n squared things, we're reusing a lot. So we want to do better than this. And that's the recursive algorithm, which we've seen. So we know the algorithm pretty much. I just have to tell you what the layout is. So we're going to take C, partition C11, C12, and so on. And so I have an n by n matrix, and I'm partitioning into n over 2 by n over 2 submatrices, all three of them. Times whatever. And I could write this out yet again, but I won't. Okay? We can recursively compute this thing with 8 matrix multiplies and a bunch of matrix additions. I don't care how many, but a constant number. We've seen that at least twice now, so I won't show it again. Now, how do I lay out the matrices? Any suggestions how I lay out the matrices? I could lay them out in row major order or column major order, but that might be less natural now. You're not doing anything by rows or by columns. So what layout should I use? Yeah. Quartet major order. Maybe quadrant major order, unless you're musically inclined. Yeah, good idea. You've never seen this order before, so it's maybe not so natural. But yeah, somehow I want to cluster it by blocks. Okay, I think that's about all I'll get. So, I mean, it's a recursive layout. This is not an easy question. It's okay. Store matrices, or lay out the matrices recursively by block. Okay, I'm cheating a little bit. I'm redefining the problem to say, assume that your matrices are laid out in this way. But it doesn't really matter. We can cheat, can't we? In fact, it doesn't matter. You can turn a matrix into this layout without too much work, linear work. Almost linear work. Log factors, maybe. Okay, so if I want to store my matrix A as a linear thing, I'm going to recursively define that layout to be recursively store the upper left corner, then store, let's say, the upper right corner. It doesn't matter which order I do these. I should have drawn this wider. Then store the lower left corner, and then store the lower right corner recursively. So how do you store this? Well, you divide it in 4 and lay out the top left and so on. Okay, this is a recursive definition of how the element should be stored in a linear array. It's a weird one, but this is a very powerful idea in cache-oblivious algorithms. We'll use this multiple times. Okay, so now all we have to do is analyze the number of memory transfers. Seems, how hard could it be, right? So we're going to store all the matrices in this order, and we want to compute the number of memory transfers on an n by n matrix. See, I lapsed and I switched to lowercase n. I should, throughout this week, be using uppercase n, because for historical reasons, any external memory kinds of algorithms, two-level algorithms, always talk about capital N. And don't ask why. You should see what they define little n to be. Okay. So, any suggestions on what the recurrence should be now? All this fancy setup, but the recurrence is actually pretty easy. So definitely it involves multiplying matrices that are n over 2 by n over 2. So what goes here? Eight. Thank you. That you should know. And then the tricky part is what goes here. Okay, what goes here is, well, okay, now the fact that I can even write this, ignore this is the matrix additions. Ignore those for now. Suppose there weren't any. I just have to recursively multiply. The fact that this actually is 8 times memory transfers of n over 2 relies on this layout. Right? I'm assuming that the arrays that I'm given are given as contiguous intervals in memory. If they aren't, I mean, if they're like scattered all over memory, I'm screwed. There's nothing I could do. So, but by assuming that I have this recursive layout, I know that the recursive multiplies will always deal with 3 consecutive chunks of memory. 1 for A, 1 for B, 1 for C. Okay, no matter what I do, because these are stored consecutively, recursively, I have that invariant. Okay, and I can keep recursing, and I'm always dealing with 3 consecutive chunks of memory. That's why I need this layout, is to be able to say this. Okay, now what does addition cost? I'll just give you 2 matrices. They're stored in some linear order, the same linear order among the 3 of them. Do I care what the linear order is? How should I add 2 matrices? Get the output. Yeah.
If they're stored in the same, if they're stored in the same fashion, then you can just add all of the n squared after n squared, n squared over.
Right. If each of the 3 arrays I'm dealing with is stored in the same order, I can just scan in parallel through all 3 of them and just add corresponding elements and output it to the third. So I don't care what the order as long as it's consistent, and I get n squared over b. I'll ignore plus 1 here. That's just looking at the entire matrix. So there we go. Another recurrence. We've seen this with n squared, and we just got n cubed. But turns out now we get something cooler if we use the right base case. So now we get to the base case, the tricky part. So any suggestions what base case I should use? The block size, good suggestion. So if we have something of size order b, we know that takes a constant number of memory transfers. Turns out that's not enough. I won't solve it here. But good guess, in this case, it's not the right answer. I'll give you some intuition why. We're trying to improve on n cubed over b. If you're just trying to get it divided by b, this is a great base case. But here we know that just the improvement afforded by the block size is not enough. We have to somehow use the fact that the cache is big. It's m. However big m is, it's that big. Okay, so if we want to get some improvement on this, we've got to have m in the formula somewhere. And there's no m's yet, so it's got to involve m. What's that? MT of m over b. That would work, but MT of m is also okay. I mean, some constant times m, let's say. I want to make this constant small enough so that the entire problem fits in cache. So it's like 1/3. I think it's actually, oh wait, is it square root of m, actually? Right, this is an n by n matrix. So it should be C times square root of m. Sorry. So square root of m by square root of m matrix has m entries. If I make C like 1/3 or something, then I can fit all 3 matrices in memory. Actually, 1 over square root of 3 would do, but who cares? So for some constant C, now everything fits in memory. How many memory transfers does it take? 1. It's a bit too small. Because I do have to read the problem in. And now, I mean, here was 1 because there's only 1 block to read. Now, how many blocks are there to read? Constant? Nope. B? Nope. M over B, good. Get it right eventually. It's a great thing about thinking with an oracle. Just keep guessing. M over B, because we have cache size M. There are M over B blocks in that cache to read each one. Okay? This is maybe you forgot what M was, because we haven't used it for a long time. But M is the number of elements in cache. This is the number of blocks in cache. Okay, someone was saying B, and it's reasonable to assume that M over B is about B. That's like a square cache. But in general, we don't make that assumption. Okay, where are we? We're hopefully done. Just about good, because we have 3 minutes. So that's our base case. Oh yeah, I have a square root here. I just forgot it. Now we just have to solve it. Now this is an easy recurrence. Right? I don't want to use the master method. Okay, because master method is not going to handle these b's and m's and these crazy base cases. Okay, master method would prove n cubed. Great. Master method doesn't really think about these kinds of cases. But with recursion trees, if you remember way back to the proof of the master method, just look at the recursion tree as geometric up or down, or everything is equal, and then you just add them up, every level. The point is that this is a nice recurrence. All of the subproblems are of the same size. And that analysis always works, I say, when everything has the same size. All the children. So here's the recursion tree. We have n squared over b at the top. We split into 8 subproblems, where each one the cost is 1/2 n squared over b. I'm not going to write them all. There they are. You add them up. How much do you get? Well, there's 8 of them. 8 times 1/2 is 2, right? 4. Thanks. 4, right? Okay. Good. See, I'm bad at arithmetic. I probably already said it, but there are 3 kinds of mathematicians. Those who can add, those who can't. Okay. Why am I looking at this? It's obvious. Okay. So we keep going. This looks geometrically increasing, right? 4, okay? You just know in your heart that if you have a recurrent, work out the first 2 levels, you can tell whether it's geometrically increasing, decreasing, or they're all equal, or something else, and then you better think. But I see this is geometrically increasing. It will indeed be like 16 the next level, I guess. Okay, it should be. So it's increasing. That means the leaves matter. So let's work out the leaves. This is where we use our base case. So we have a problem of size square root of m. And so we plug that in. Yeah, your question?
Why is it at n squared over b if you plug in n over 2?
Oh, indeed. I knew there was something. I knew it was supposed to be 2 out here. Thanks. This is why you're here. It's actually n over 2 squared over b. Thanks. I'm substituting n over 2 into this. Okay, so this is actually n squared over 4b. So I get 2, because they're 8 times 1 over 4. Okay, I wasn't that far off then. It's still geometrically increasing. still the case, okay? But now it actually doesn't matter. Whatever the constant is, as long as it's bigger than 1, great. Now we look at the leaves. The leaves are root m by root m. I substitute root m into this, I get m over b. Some constants, who cares? So each leaf is m over b. Okay, lots of them. How many are there? This is the only... If you deal with recursion trees, counting the number of leaves is always the annoying part. Oh boy, well, we start with an n by n matrix. We stop when we get down to root n by root n matrix. So that sounds like something. Oh boy, I'm cheating here. Really? That many? Sounds plausible. Okay, the claim is, and I'll cheat. So I'm going to use the oracle here, and we'll figure out why this is the case. N over root m cubed leaves. Okay, why? I think here it's hard to see in the tree, but it's easy to see in the matrix. Let's enter the matrix. We have our big matrix. We divide it in half. We recursively divide in half. We recursively divide in half. You get the idea, okay? Now, at some point, these sectors, let's say one of these sectors, each of these sectors fits in cache, and 3 of them fit in cache. So that's when we stop the recursion. In the analysis, the algorithm goes all the way. But in the analysis, let's say we stop at m. Okay? Now, how many leaf subproblems are there? Oh man, this is still not obvious. Okay, the number of leaf chunks here is like, the number of these things is something like n over root m. Right, the number of chunks. But it's a little less clear because I have so many of these. But, all right, so let's just suppose now I think of normal, boring matrix multiplication on chunks of this size. That's essentially what the leaves should tell me. I start with this big problem. I recurse down to all these little tiny, multiply this by that. Okay, this chunk, this root m by root m chunk. Okay, how many operations, how many multiplies do I do on those things? N cubed. But now the n, the size of my matrix in terms of these little submatrices, is n over root m. So the cost, so it should be n over root m cubed subproblems of this size. If you work it out, normally we go down to things of constant size, and we get exactly n cubed of them. Now we're stopping at this short point and saying, well, it's whatever, however many there are, cubed. Okay, there's a bit of hand waving. You could work it out with the recurrence on the number of leaves, but there it is. So the total here is n over, let's work it out, n cubed over m to the 3/2, that's this number of leaves, times the cost of each leaf, which is m over b. So some of the m's cancel, and we get n cubed over b root m, which is a root m factor better than n cubed over b, which is actually quite a lot. Square root of the cache size. That is optimal. The best two-level matrix multiplication algorithm takes n cubed over b root m. Memory transfers. Pretty amazing. And I'm over time. You can generalize this and do all sorts of great things. But the bottom line is this is a great way to do matrix multiplication is recursion. We'll see more recursion for cache oblivious algorithms on Wednesday.